Hello again and welcome to the BAXEDM YouTube channel. The channel that gives a YouTube video series on how you can make your own wire EDM machine. Today on part 5 I will zoom into the mechanics of my example machine, and specifically the mechanics that do not involve wire handling. As the wire handling mechanics I will cover those in part number 6 following this part. First today we'll have a look at my CAD model, and I'll zoom into some details that require additional attention. After that I'll show you some footage of the mechanics of my actual machine and zoom into the same details as well. And that's it for today. So sit back and I hope you enjoy. Okay, I was going to show my CAD model by using a screen capturing program. However, that did not seem to work together with CAD at the same time, so struggled a bit with it. Eventually decided just to capture it with my video camera, because I know a lot of you people are waiting for a new video, and otherwise it would just take too long for me to figure everything out why it wasn't working. So here's my CAD model, and I want to take you through it. You can download the CAD model on BAXEDM.com. And okay, let's have a look at it. So the first thing I want to show here is the axes. So this, what's highlighted right here, that's the y-axis, and this is the x-axis. The first thing to note is that the y-axis is mounted to the frame by 3 legs, 1, 2, 3, and 1 plate. So why is it not mounted on 4 legs? Well, think of it. If you have a floor that is not really flat, and on top of that floor you put a really flat table, with 4 legs it will always wobble. And then if you do not like the wobble and bolt the legs to the unflat floor, you will force the table to be unflat as well. Now the y-axis here is a really nice and flat piece of mechanics, and the frame is a welded frame, and welded frames always warp and tend not to be very accurate. So we have an unflat floor and we have a flat y-axis, and then we need to bolt these things together without distorting the y-axis. How do you do that? Well, first you use your standard 3 legs, 1, 2, 3, and this makes sure that you do not wobble. And then instead of a leg you use a plate. So this is the plate, and the plate should not impose a height here. So if you bolt the plate to the side and you use these slots here, so the plate can move freely before you bolt it fixed, and then you can bolt something that is nice and flat to something that is not flat. Now this works really well, but if there's a large temperature difference between the frame and the y-axis, then you get a lot of forces here because one distorts the other. However, since both are in the same machine and reside in the same environment, it's not likely that there's going to be a temperature gradient, and then under those boundary conditions this will work quite well. So that is the first thing you should keep in mind. How to bolt something that is nice and flat to something that is unflat. Another question is, how do you get the y or the x-axis, which are just a copy of each other and stacked on top of each other, how do you bolt them together, or how do you bolt a single axis such that it is flat? Well, first you need to make these end blocks, these precision end blocks. You need to do that on a milling machine, and you need to make sure that the holes in the block are perfectly parallel to each other. So if you machine these holes, make sure that the workpiece, this block, resides in the workpiece clamp. Do not machine one hole and then take the block out of the clamp and turn it around or do things with it and then try to machine the other hole. No, machine both holes in one go. So you know for sure that within the accuracy of your milling machine, these holes are perfectly parallel. Now then you make two blocks and then you stick in these rods, so the linear guides. You stick them in, but you do not tighten these fixation screws. So everything is then only loosely connected together. Then you need to put the whole thing on something that is really flat. Well, it would be nice if you have this granite super flat table, but most of you do not have that. So the only thing that is really flat, which is accessible by most, is the table of a milling machine. So take off your vise, your clamp of your milling machine, clean the table and put the whole thing, the whole axis, on top of the table. Then clamp the end blocks, these blocks fixed to the table, and then you know for sure that the front and back block are aligned in the same plane and are really straight, flat, exactly parallel. And only then you tighten these screws. You tighten them really strong, and then you have your flat X or Y axis. You can do both in the same way. And then it's time to stack the Y axis on top of, then you stack the X axis on top of the Y axis. So basically you just stack them on top of each other, and then underneath this block here there's a pin. There's a pin that is exactly in the middle, so that if these bolts in this star configuration, if these are unscrewed, then the top axis, the X axis, can rotate along the center pin relative to the Y axis. And then if you just bolt the screws tight, you're pretty sure that the X and Y axes are not parallel, not perpendicular to each other. So this requires an alignment procedure. So first you should find a block or hunk of steel that has two exactly perpendicular faces. And then you take the block and you clamp it against the Y axis here, such that one side of the block is along the axis and the other side is along the X axis. And then you clamp a measurement gauge, micrometer or something, you clamp it against the end block of the X axis and you move the X axis up and down while the probe, the feeling part of the gauge, moves along the face of the block that is mounted exactly against this axis. So then if the X axis and Y axis are not perfectly perpendicular, you can see that your gauge will walk away, or will change when the X axis moves. And then it's time to take out your rubber hammer and ever so slightly tap the end of the X axis back and forth, and then move the X axis again, move them up and down, tap, move it up and down and tap. And that takes quite some time. Took me more than half an hour before everything is aligned in such a way that the X axis is perfectly perpendicular to the Y axis. And then you tighten the bolts, but tighten the bolts in a crosswise manner, and even then this is going to affect your perpendicular accuracy. So even during tightening, small taps of a hammer are required. And then again you tighten a bit more, you tap a bit more, you tighten a bit more. And then eventually, after an hour, but you only need to do this once. The X and Y axes will be perfectly perpendicular to each other. So that's how you align them. So next, let's talk about the workpiece table. So the workpiece table is mounted to the frame with the use of flexures. So let me show it here. This is a single flexure. A flexure like this imposes a limit to a single degree of freedom. So it fixates, I should say, a single degree of freedom. So along these axes, the stiffness of this little rod is super high. So if you want to move along the Z-axis here, it's super stiffly connected to the frame. But rotation around this point, any rotation along the Z-axis, the X-axis or the Y-axis, can be done freely because this little thing can easily bend. The same holds for translations around, or translations along the X-axis and the Y-axis, because it can slightly bend like this. So you only impose a single degree of freedom. Because that is exactly what we want. We want to mount the workpiece table to the frame, and we do not want to over-constrain the degrees of freedom. So for each degree of freedom that the table has, there should be a single fixation. And that's why, because we have 6 degrees of freedom, X translation, Y translation, Z translation, and 3 rotations along X, Y, and Z. So we have 6 degrees of freedom for the table, and that's why we need to fix it exactly in 6 points. So 1, 2, 3, turn it around, 4, 5, and 6. And each can be adjusted. So each of these degrees of freedom, they rest on this little pin, which has fine metric thread on it. And yeah, you can unscrew these bolts and then adjust the whole length along the axis of the flexure. And then you can set adjust the height of the single fixation point. And because you can do this for all points, you have full control over all degrees of freedom of the workpiece table. Now the workpiece table, let me hide the tank here, that's more convenient. Alright, so the tank is hidden. The workpiece table is constructed from 2 pieces of rectangular stock. And the rectangular stock is not flat, it's always a bit bent. So grooves are machined into the stock to make sure that the groove is perfectly straight. And also the 2 pieces of rectangular stock are fixated against each other by these 2 screws. And the faces that rest against each other are machined as well, so that you know that the 2 pieces of stock are exactly perpendicular to each other. And then you can adjust all screws by gauging. So you need to move the axes back and forth and back and forth. Then you can select rotation axes. Or you can adjust your rotation, you can adjust, or you don't need to adjust the translations. You don't need to adjust your X, Y, and Z translations. Z is not relevant because that's the height of the workpiece. You can set it by eye, that's good enough. Then the X and Y translations are not really relevant because you can basically choose them with your machine. The machining does not home against some end stops, so that you always know exactly where your absolute position is. So then X and Y are not relevant. But what is really relevant are the Rx, Ry and Rz degrees of freedom. And that is what you set by adjusting the alignment screws here. So rotation along the Z-axis, rotation along the Y-axis and rotation along the X-axis. If you do that properly, then you can make sure that if you put a perfectly perpendicular piece of stock onto your workpiece table and you machine a square hole in it, then all faces of the hole, of the inside hole, will be exactly perpendicular to the faces of the outside of your nice square piece of stock. So I think that's preferable. There are also other ways of doing it. For instance, if you have a rotation along your Z-axis, you can measure the rotation first with the gauge by displacing a known distance, and then measure how much the displacement is. You can calculate what the rotation is of the workpiece, and then in your CNC code, G code, you can do a coordinate transformation and correct for that problem. But yeah, although that's possible, it's not really preferable, because you need to figure that out for each workpiece. Not really nice. Okay, what are some other details? I'd like to quickly discuss the ball screw spindles and how they are mounted inside the machine. So the ball screw spindles, just like the story I told about the table with the 4 legs, for a ball screw spindle you also want to mount it in such a way that the degrees of freedom are not over constrained. So one end, and preferably the outside end of the ball screw spindle, should be able to move freely along the Z-axis, and the other end should be supported along the Z-axis, because the axial forces, what you call them, they need to be diverted to the frame. So there are 2 different bearings. One is an angular contact bearing that is below this block. So the angular contact bearing supports axial as well as radial forces. So the spindle is fixated in this point. So this small block here fixates the bearing inside the main block. I can hide it. It's gone. Okay, so here you can see the bearing. And the bearing is not mounted flush with the block. It slightly sticks out. And then if you screw another block against it, you press it such that it cannot move along the direction of the axis. Then it's fixated. And then here's a small sleeve which is threaded inside, and it's bolted against the bearing. So then the ball screw spindle is pressed into the bearing and fixated against the bearing. So that's how the axial forces are diverted to the frame. And the other end is freely suspended, at least along the axis, but there is a bearing to take away the radial forces. And then you could say, well, then you're over-determined as well. Yes, that is true, but because this rod is so long, it can easily move by a small amount without generating a lot of forces. What's also nice to mention is the supports of the workpiece table and how they create water tightness, because they run straight through the tank. Let me show the tank again. Okay, here's the tank. So the workpiece table needs to be electrically isolated from the frame. And it needs to be really, the connection between the flexure and the workpiece table needs to be super stiff. If you were to use plastic here, it's not stiff. and plastic tends to creep. So if you put weight on it, it slowly crimps. You don't want that because then you lose accuracy. So you need to have something stiff and isolating, which is a ceramic material. So I used ceramic legs that connect the stainless steel workpiece table to the flexure here. And around the ceramic leg I made a silicon seal, which is a custom seal. So first I 3D printed a mold in which I poured silicon, and when that cured I was able to slide it over the ceramic leg, and then yeah, it has a collar, and the collar is pressed against the bottom of the tank with this plastic 3D printed part. It's a nice detail. It really works well, keeping everything watertight, and the complete tank is actually it's free, so you can move it around by a few millimeters, which is the distance between the clamp and the ceramic leg. That's a nice detail. Now the whole assembly for handling the wire, I will cover that in the next part, because that's also quite a long story. I'm not going into details right now. And the last thing I want to discuss is the legs on which the frame is resting. So I'm using a standard stainless steel tubing here, and I TIG welded the frame, and it's resting on these legs, which I made myself. The legs use a point contact, as you can see, and these are adjustable, so I can adjust the height. So ideally, in the beginning, I wanted to have my machine only on 3 legs to make sure it's not over constrained. However, that's not going to work, because the center of mass shifts quite a bit, and then it also, if you put a lot of water in the tank, the weight distribution changes, and then yeah, it starts to get unstable. So I needed 4 legs. So how did I adjust this? Well, first I put it on 3 legs, and I make sure that the center of mass is such that it can actually rest on 3 legs without tipping over. And then I put the 4th leg underneath and gently raise the support until it just touches the tip, and then yeah, basically that's it. Although it is overdetermined, not much more you can do about that. Okay, that's it for the CAD model. Let's have a quick look at the actual mechanics. Okay, now that we have seen the CAD model, let's have a look at it in real life. Okay, first the details. Let me show you the flexures that I was talking about. So here's an example, and the flexures are actually, the thin rods are actually thick filler wire, and these are brazed into the brass bodies, and I brazed it with the silver solder. That actually works quite well. As you can see here, these have a really fine pitch thread, so you can really fine tune the settings. And the ends of the rods here, my CAD model did not have it, but I actually machined a hexagonal shape on it here, so you can fit a small spanner to it. Then you can tighten the bolts and keep with the spanner the center rod from torquing, which is nice. Then it doesn't mess up your fine adjustment. So that's on the corner. I have one there as well, and here on the inside. cannot dive in with my camera here, but there's one there as well, or two actually. Okay, then the angular contact bearing. I also forgot to mention in my CAD model that I'm using these things. These are also used to mount the motor such that it's not over-determined, because this body and this body are not rigidly connected to each other. They're connected by this rubber block here, so a slight misalignment of the motor is allowed. And the nice thing about this is that it does not only fix alignment problems, it's also a damper. So each stepper motor has a torque ripple and a resonance frequency, which has some bad effects, and part of those effects you mitigate by putting a damper in between the thing you drive and the motor itself, which is this rubber block. So that's really nice. Then the water seals. Well, they're a bit dirty because those are typically these places that are hard to reach. But it's better to show from the inside. Zoom in here. So there's a water seal. And as you can see, I can move around the tank. So the tank is absolutely not fixated to the workpiece table or to the ceramic rods here. This is the ceramic rod, the white piece. And here's my adjustment leg. In the CAD model it's upside down. I actually flipped it in my actual machine because I found this to be more convenient. So I can rotate this, and I can lock it here. This is a locking screw. So once it is adjusted, I can lock it in place. Here's a top view of the axes stacked on top of each other. And the plate in the back that I also discussed in the CAD model. Yep. Well, that's basically it. That's it for part 5 of this series. Make sure to subscribe to this YouTube channel, because then you will not miss out on episode 6, the next one, where I will explain the mechanics of the wire handling mechanism. See you next time.